For section 3.7, we are going to be focusing tonight on, or today, on permutations and combinations. So we're going to take a quick look at just a small example. We've got a small menu of items, 3 appetizers and 2 desserts. If you can choose exactly one of each, how many different possibilities do you have of what you could order? So just to kind of get a picture of this, let's just name our 3 appetizers: appetizer 1, appetizer 2, and appetizer 3. So after we have chosen one of those 3 appetizers, then we also have a choice of 2 different desserts. And to be just as creative, let's call that dessert 1 or dessert 2. So if we pick appetizer number 1, we've got 2 choices for desserts. So we've got appetizer 1 with dessert 1 or appetizer 1 with dessert 2. But if we choose appetizer 2, we still have our 2 options for desserts. So we could choose appetizer 2 with dessert 1 or appetizer 2 with dessert 2. I'm having a hard time saying that word today. And then if we chose appetizer 3, we could also choose dessert number 1 or dessert number 2. So what we notice in this situation is that we have 1, 2, 3, 4, 5, 6 different total options that we could choose by picking one of the 3 appetizers and one of the 2 desserts. So 6 different options is what we would have there. And this leads us into something called the multiplication principle, or the basic counting principle. And what it says is, if you have a certain number of options for one choice and a certain number of options for another choice, all you would have to do is multiply those 2 sets of options together, the amount of options you have. And so in our case, that would be 3 times 2, and that would give us the 6 as well. So we're going to see that on the next slide here as we look at this rule. The basic counting rule. Suppose there are m number of choices for the first category and n number of choices for the second category, p number of choices for the third category, and so on. Then the total number of available choices is m times n times p times whatever other options that we have. So this is also sometimes called the multiplication rule for probabilities. Example 3.24. Suppose at a particular restaurant you have 8 choices for an appetizer, 11 choices for a main course, and 5 choices for dessert. If you are allowed to choose exactly one item from each category for your meal, how many different meal options do you have? This is where that multiplication principle comes in. We've got 8 choices for the appetizers times 11 choices for the main course, and then 5 choices for the dessert. So all we would have to do is take 8 times 11 times 5. So I'm going to grab my calculator and take care of that. 8 times 11 times 5, and we get 440 different choices. So that's how the multiplication principle works, or the basic counting rule. Pretty straightforward as long as you are choosing one from each of those groups. Example 325. There are 21 novels and 18 volumes of poetry on a reading list for a college English course. How many different ways can a student select one novel and one volume of poetry to read during the quarter? So again, same principle here, 21 different novels to choose from times the 18 different volumes of poetry to choose from, and we're going to multiply those together. 21 times 18 will give us 378 different combinations of books and poetry that we could choose for that quarter of reading. Example 326, how many different ways can the letters of the word math be rearranged to form a 4-letter code word without using one letter more than once? And this doesn't mean that it actually has to be a word, it's just a code of some sort. But notice how many different options we have for the first letter. Well, there are 4 different letters to choose from. So for the first letter that we're going to use, we have 4 different options. But once we've used one of those 4 different options, whether it's the M, the A, the T, or the H, we only have 3 letters left for our second choice because we are not using any letter more than once. And after we've used the first 2 letters that we've chosen, there's only 2 options left for the last one, or for the third option. And then once you've chosen the first 3 letters, there's only 1 option left for the last one. So if we multiply this together, 4 times 3 times 2 times 1, we get 24 different arrangements of the letters in the word math that you could use as some sort of coded, I don't know, password or something. But 23, and that's that same counting principle. You can multiply by the number of options that you have for each group. So for first letter, you've got 4 different options, but then for the second letter, you've only got 3 options left. For the third letter, you've got 2 options left, and then for the fourth one, there's not really a choice because you've already used the first 3. There's only 1 option left there. So that's kind of the quote-unquote groups when you're looking at this, is just the letter of the blank that you're putting it in. This leads us to a definition and some special symbols in math, and this is called factorial. So let n be a positive integer, then the factorial symbol, which is an exclamation point, is defined as follows. N factorial equals n times n minus 1 times n minus 2 times n minus 3, and so on and so on and so on, until your numbers get smaller and smaller, and eventually you get to 2 and 1, and then you are done. By definition here, we can see that 0 factorial equals 1, and also 1 factorial equals 1. And those are definitions that we're going to have. So just for example, that last one that we did would have been 4 factorial. And what that means is 4 times, and then you take 1 away from 4, and that gives you 3. And then you take 1 away from that, and it gives you 2. And then 1 away from that, and it gives you 1. And once you get to 1, you stop. And so that's what 4 factorial means, or any factorial. You start with the number that you're given, and then you go down until you get to 1. You go down by 1 and keep multiplying until you get down to a 1. So example 327, how many ways can 5 different door prizes be distributed among 5 different people? Okay, so if you think about that situation again, you've got the first person could get one of the 5 door prizes, so they have 5 options. Once that person has gotten their prize, the second person chosen has only 4 options left. And once that person has gotten their prize, the third person only has 3 choices left. And the fourth person to get theirs only has 2 choices left, and so on. So we can see that same pattern. So this would be 5 factorial. Now there is a button for this on your calculator. You do not have to do this by hand, especially that would be a pain if you had like 15 factorial and you had to do 15 times 14 times 13 times 12 and so on. So I'm going to pull up the calculator and I'm going to show you how to do 5 factorial on your calculators. So I know you can't see our 5 factorial anymore, but this is how we would do this on the calculator. We've turned our calculator on. We have to put in the 5 first, and then we're going to go up here to the math key, and then we're going to go over all the way to the right to the PRB, the probability menu, and you'll look down there and you'll see that number 4 is the exclamation point, and so we're going to put that in, and so we see 5 factorial, and we hit enter, and we get that 120. That would be the same as if we did 5 times 4 times 3 times 2 times 1. And those are the same answers. So that's how we would do factorial on our calculators. We're going to be using that menu right there, the math and then probability menu, for several different things. In this lesson, we're going to be using those 3 most of all. The NPR, the NCR, and the factorial. We'll come back to what those other 2 mean. But that's how we do factorial. Example 328. 8 sprinters have made it to the Olympic finals in the 100-meter race. In how many different ways can the gold, silver, and bronze medals be awarded? So notice that for the gold, we have 10 different people who could win, or sorry, not 10, 8 sprinters. So let's change that. We have 8 different people who could win the gold. Once that gold person has, once the one person has won the gold, then for silver, we would have 7 people left there. And then for bronze, we would have 6 left. So notice this is not a factorial. This is just 8 times 7 times 6, but it kind of has that pattern of a factorial situation. And that leads us into another situation that we've got, and that is what we call permutations. So permutations are situations, and we're going to look at the technical definition in a minute, but there's situations where the order matters, or there's some sort of differentiation between the values. So notice we've got gold and silver and bronze. You know, a person getting first place or getting third place, that's different because one of them would get a gold and one would get a bronze. So the order that they finish in this case, is going to matter. And so the way we do this permutation, and this is this NPR that we just saw, but the N is the total number of options we have to choose from. And in this case, it's the 8 sprinters that we have. And the R is going to be how many of them we are selecting. And in this case, it's 3 because we're going to select a person to get gold and silver and bronze. So 8P3. And when we do that, that's going to give us this number, 8 times 7 times 6. And I'm just going to multiply that here first, and then we'll look at it on the calculator. 8 times 7 times 6 is 336. That's using our multiplication rule, or our counting principle. To show you how to do this on the calculator, what we have to do is we're going to have to put in the 8 first from the 8P3, and then we're going to go to our math button again and go over to PRB, and we're going to choose that second option for a permutation, and then we're going to put in the 3. And we're going to hit enter, and that will give us the same 336 that we had when we did it by hand. So that's going to be another valuable tool for us, that we can have the calculator do some of this work for us. So now the technical definition for a permutation: if R number of items are selected from N number of choices without replacement, we call this ordered arrangement. So that's going to be the key thing here. The order will make a difference. A permutation. The notation we use is NPR, your subscript N and R. And by definition, if we were going to do this by hand, it would be N factorial divided by N minus R factorial. We're not going to do that by hand, but again, we could. But we have our calculators to help us out, and they will take care of doing that math for us. Note with permutations, the order matters. That is very important. So for example, it might be first place, second place, third place. It might be differentiating the order by like ranking, president, secretary, treasurer. So something like that. The order of the selection makes a difference. Secondly, the selections are chosen without replacement. Those are the 2 things that are necessary for permutation. So you cannot use the same value over again. And again, looking back at our 2 things here, the order matters. You couldn't have a person getting first place and second place both. You couldn't have a person who was elected to president and secretary both. So those are the types of things we're looking for here with permutations. Example 329, in how many ways can people in a 1,000 person marathon finish first, second, and third? So the fact that they are differentiating here, the order matters, first, second, and third, tells us we are dealing with a permutation. So to set this up, I'm going to put my P there for permutation. Right away, we know we're selecting 3 different first, second, and third place people. And then how many do we have to choose from? Well, we have any of the 1,000 people in the race that could finish first, second, or third. So that's going to be 1,000 P3. So let me pull up the calculator again. So on the calculator, I'm going to put in 1,000, and I'm going to go to the P, so math, over to PRB, and then NPR. And we're going to put in the 3 for how many people we are selecting. And notice we've got a large number there. So 997 002 000. So 997,002,000 different ways that people could finish first, second, and third. And that is the answer for 3.29. Example 330. How many 5-character passwords can be made using the letters A through Z if repetition of letters is allowed? Then what about if repetition of letters is not allowed? And then what is the difference between these two scenarios? So if repetition is allowed, then we would just use our counting principle. And hopefully we will remember, so with repetition, we would have 26 options for the first letter. We'd have 26 options for the second one, 26 for the third one, 26 for the fourth one, and 26 for the fifth one. And we would just multiply these all together, and I'll do that in just a second. But without repetition being allowed, so we can't use the letters more than once, we would have 26 for the first one, but then only 25 letters left for the second choice, 24 left for the third letter, 23 left for the fourth, and then only 22 left for the fifth one. And we would multiply those together. So notice this one is an NPR situation, and we would do 26P5. This one is just multiplication. We're going to take 26 and raise it to the 5th power. 26 times 26 times 26, and then 5 times. So let's take a look at this on the calculator, and then we'll find the difference between those two. So for the first one, we've got 26 times itself 5 times. We can write that as 26 raised to the 5th power and hit enter. So that gives us 11881376. Then for the second one, we are not allowed to use repetition, so that we can do our 26. We can go to Math, over to the NPR in the probability menu, and then we're going to select 5 of those 26 letters, and we're going to get 789 3600. So this is with repetition, and this is without repetition. So that's this one and this one. And then the question was, what's the difference between those? Well, difference means we subtract. So we're just going to take the bigger one, the 11881376, and subtract the smaller one, the 7893600. And we're going to get that the difference between the two is still a pretty large number. The difference is 3987776. So there are 3,987,776 more options if we allow for repetition. And so when you're doing passwords, you usually will allow for that repetition because you want as many different possible password or passcode combinations as possible. Besides permutations, we also have what are called combinations. And if our items are selected from n number of choices without replacement, we call this arrangement a combination. Now notice there's no ordered arrangement here. For permutations, the order mattered. In combinations, the order is not going to matter. And I know that seems a little bit deceptive because when we think about combinations, we think of like combinations on a lock or a padlock or something, and the order that you would type them in would make a difference. But in statistics, when we talk about combinations, the order does not matter. So notice the formula is fairly similar to permutations. If we were going to do it by hand, there's just this one extra piece to it, the r factorial. Again, we're not going to do this by hand. We're going to let the calculators take care of this for us. So a couple things we want to note about combinations. The order does not matter. Very important here. If the order does not matter, you're dealing with a combination. If the order does matter, you're dealing with a permutation. So for example, selecting two team captains out of a group, selecting four committee members, where there's no ranking of those things. It's just you're putting a group together. A lot of times you'll see the word group. You may even see the word combinations. The selections are chosen again without replacement. You're not allowed to use any item from the group more than once, or from the selections more than once. Example 331, the United States Senate Appropriations Committee consists of 29 members. The Defense Subcommittee of the Appropriations Committee consists of 19 members. Disregarding party affiliation or any special seats on the subcommittee, how many different 19-member committees may be chosen from among the 29 senators on the Appropriations Committee? Well, this, just to kind of clarify, this means that everyone in the group is basically the same. Now, that's not in reality how it works, but in our example here, that's what we're going to do. And that means the order doesn't matter. It doesn't matter what order they get put on the committee. They are in the committee, and so that makes this a combination. And so I'm going to put my C here. Notice we have how many different senators to choose from? We have 29 senators to choose from. So that's going to be our first number here. And then the number after that, the amount of senators that we're going to choose to be on this subcommittee, are the 19. So we would have 29C19. And let's go ahead again and pull up the calculator to do this work. And I know you can't see that anymore, but we know that it was 29. And then to get to the C, we go to the math key again and over to PRB for the probability menu. We're going to go down to number 3, NCR. And then we put in the 19 that we want to choose. And again, we get pretty large numbers here. There are, we've got 200, 300, 10. So 20 million different ways, 20,030,010 different ways that we could choose that 19-person subcommittee group out of the 29 senators that are already on the Appropriations Committee. Example 332, a 4-digit PIN number is selected. What is the probability that there are no repeated digits? Okay, so we have changed things up a little bit here. Now we're looking for probability, and we're looking for probability of no repeated digits. So we're going to go back to this idea of favorable outcomes over total outcomes. So again, favorable doesn't necessarily mean good. It just means what we're looking for in this situation. So if we are looking for no repeated digits, the way that would happen is we would have 4 digits to choose, and we have 10 digits to choose from, 0 through 9. And so we would have, if you think about that, that is a permutation, because the order is going to make a difference. So we're going to have 10 different choices to choose from. We're doing a permutation of 4 of them. Then the total, if you think about how many total options there are where we do allow repetition, that's going to be 10 for the first option, 10 for the second, 10 for the third, and 10 for the fourth. So I think we've done enough of the permutation and combination stuff. So what I'm going to put into my calculator here is 10P4 for the top number, and I'm getting a pretty big number. It is 94109,400 divided by, and then on the bottom I'm going to put in 10 raised to the 4th power, which is, oh, whoops, I put in 100P4. That is not going to work out. So let's put in 10P4. That'll be much better. 10P4 is going to be 5,040. So for those of you who are wondering how I got that gigantic number, it's because I typed in the wrong number. I typed in 100P4. Then 10 raised to the fourth power for the bottom is going to be 10,000. And we just divide those two to find the probability. So 5,040 divided by 10,000 gives us 0.504. So there is just a little bit over a 50% chance that there are no repeated digits if we would randomly select a 4-digit PIN number. Example 333, Bucky told Satchel that he would give him a hug, a big hug, if he drew 3 aces and 2 5s in no particular order. What is the probability, again, probability, that Satchel draws this 5-card set? So again, we're going to have favorable over total. Well, the total might be the easiest one to do since we're picking a 5-card set and the order doesn't matter. We're dealing with a combination. So we have 52 cards to choose from our deck of cards that we've been talking about, a whole bunch, and we're going to choose 5 of them. Now, when we have 3 aces, if we're going to pick 3 aces, we have to remember that it is still a combination. The order that we choose them in doesn't matter. And we have 4 aces to choose from, and we're going to select 3 of them. And how many different ways could we do that? And then the counting principle, how many different ways could we choose 2 5s? Well, we once again have 4 5s to choose from, 5 of 8, 5 of hearts, 5 of diamonds, 5 of clubs, 5 of spades, and we are going to select 2 of them. So putting these numbers in, if you plug into your calculator 4C3, that's going to come out to be a 4. If we put into our calculator 4C2, that is going to give us 6. So 4 times 6 on the top is 24. And then on the bottom we have 52C5. And so we're going to put that in, and that is a really big number. 2598960. 2598960. Now I'm going to pull up the calculator because I do want you to see what happens in a case like this when we type this fraction in. So if we are going to type in 24 divided by 2598960, this is what the calculator will tell us. It will tell us 9.23. We can see that 9.23 right here, but then we see this e with a -6 by it. That e with a -6 by it actually means times 10 to the -6th power. And if you remember back to math, whenever you took an algebra-ish class, 9.23 times 10 to the -6th power means this getting divided by 10 a whole bunch of times, and we move the decimal point over to the left 6 spaces. So 1, 2, 3, 4, 5, 6. And all those spaces that we move it get filled in with zeros. So that number is actually 0.0000923, which means it is an incredibly small probability that this 5-card set gets chosen randomly. It's just not going to happen very often. So Bucky or Satchel may or may not like that. He's not going to get his big hug probably from Bucky. And but one thing again to always look for on your calculators is look for that E. Remember, your probabilities cannot be bigger than 1. So if you see 9.23, that's a hint that you probably have a scientific notation that you have to look at there. Example 334. In a certain state's lottery, 48 balls numbered from 1 to 48 are placed in a machine and 6 of them are drawn at random. If the 6 numbers match the numbers that a player has chosen, the player wins $1 million. In this lottery, the order in which the numbers are drawn doesn't matter. So that is going to be a key thing for us. The order does not matter. What is the probability of winning the $1 million prize if a single lottery ticket is purchased? All right. Well, first of all, let's figure out how many total options there are. We have 48 balls to choose from. And this is a combination because the order does not matter. And we are going to select 6 of them. Now on the top, we have to figure out how many winning selections we will have. Well, in order to win, you have to pick all 6 of the numbers that the machine picked. So you have 6 balls to choose from, and it does not matter, so it's a combination what order you pick them in, but you do have to pick all 6 of them. And if you do a 6C6 on your calculator, you're going to find out that that equals 1. There's only one way. If you've got 6 balls to choose from, the winning balls, and you're going to pick all of them, there's only one way to do that. And then we've got our bottom number, 48C6. And that is going to be a very large number. 1, 2, 2, 7, 1, 5, 1, 2. So let's see. What is the probability? We're going to go ahead and divide that. And we're going to get, again, 8.15, if we round that off to 2 decimal places after that, times 10 to the negative 8th power. And again, remember that what that means. It means 0.000000815. If we put it into normal notation, which again is an extremely small value. For example 335, it's our same situation that we just had, but in the state lottery from the previous example, if 5 of the 6 numbers that are drawn match the numbers that a player has chosen, the player wins a second prize of $1,000. So what is the probability of winning second prize? So again, probability favorable over total. The total is still going to be, what do we have, 48C6. And that's how many different ways you can draw that. Now, if you're going to draw 5 out of the 6 winning numbers, you've got 6 numbers to choose from, and you've got to get 5 of them. But then we have this one additional piece that we didn't have last time. We've got to draw one more card, but we have to make sure, or one more number, but we have to make sure that it's not a winning number. So if there were 48 winning numbers, 48 total numbers and 6 winning numbers, that means 42 are non-winning numbers, and we have to select one of those. So we're going to multiply these together. 6C5 is actually going to be 6, and 42C1, if you do that math, that's going to be 42. And then on the bottom, we have that same number that we had before, but I don't remember what it was, so 48C6. 122 71512. So I'm going to take 6 times 42 and then divide by 122 71512. And we get 2.05 times 10 to the negative 5th power. And again, what that means is you've got 4 zeros before your first non-zero digit, and then you've got your 205 after that. So still not a great chance. If they want scientific notation, that would be the top number. If they want normal standard notation, that would be the bottom number. So that is example 335. Now 3.36, suppose that 10 people are in a room. What is the probability that there is at least one shared birthday among the 10 people? So at least one, remember we've seen this a couple times, the probability of at least one means 1 minus the probability of none. So we're going to first of all focus on this and figure out what are the chances that everybody's birthdays are different. So for the first person who walks in the room, their birthday could be any one of the 365 days out of the possible 365 days of the year. When we come to the second person who walks into the room, their birthday cannot be the same as the first person, so they only have 364 more days that they can choose from, but still out of the possible 365 days. When the third person comes into the room, 2 of the days out of the year have already been chosen, so there's only 363 days left out of the year that their birthday could land on, as long as it doesn't match up with any of the other 2 out of the 365. And hopefully you're going to see the pattern here. The next person would have 362 out of 365. And so what happens is this top is 365, whoops, 365 P10, because that's going to continuously go down by 1 each time. And on the bottom, we have 365 raised to the 10th power. So let's pull up the calculator to do this. It'll be a little bit easier to see these numbers. So for the top, we're going to have 365 P10, and that's a pretty big number. That number times 10 to the 25th power. And then we're going to have 365 raised to the 10th power for the bottom. And we need to divide these two numbers. So what I'm going to do is, I'm actually just going to type these in. So I'm going to put in parentheses 365 P10, close my parentheses, and then divide by 365 raised to the 10th power. That's going to be a little bit easier to do that all at one time. And we get 0.883. So the probability here is 0.883, but we're not done. That's the probability that nobody has a matching birthday. So what we need to do to find out the probability of at least one is we're going to do 1 minus that 0.883. And when we do that, you can see my answer over here. I'm cheating a little bit, but 1 minus that answer is going to be 0.117 when we round that off. That is the end of section 3.7. You've got those 8 graded problems that you can work on, some combinations, some permutations, and then some of the counting principle. Make sure you send me a message if you get stuck, and I will try and help you out with those if I can.